Go. Thank you, Nico. Well, good morning, everyone. So it's a pleasure to be hosting this seminar of Peter Saalfrank. So Peter Saalfrank has been a visitor of the IPC, a regular visitor, I would say, in the last years, and we are really happy and privileged to have you here, Peter. So Peter is chair of theoretical chemistry in the University of Potsdam in Germany. Actually, he made his PhD in Erlangen, as far as I remember, and then, well, he has been in many places all over the world, several appointments in Germany. Before that, he also was a postdoc in Berkeley, as far as I remember. He was also a lecturer at University College in London. So he's a theoretical chemist. As I said, there are many points of contact with many of the activities that are also going on at the IPC. So thank you very much for spending this time with us, Peter. I hope that there will be future visits soon, even if, let's say, we have some constructions that they may make the stay not that peaceful, but I hope that scientifically will be equally exciting. So thank you, Peter.
Okay. Yeah, thank you very much, Ricardo, for the introduction, also for the constant hospitality here. It's always a pleasure to be here. I'm sorry, I have to apologize for the weather, because obviously I'm responsible for the rain. Whenever I am here, it's raining. And I landed here, there was even a thunderstorm around Hondarribia, so I thought, okay, this is the right start again. Anyway, so today I will talk about a topic which we started some 5 years ago. It has to do with molecules in cavities, and the slightly provocative title is Photochemistry without light. Before I start, let me thank mostly Eric Fischer. He is an excellent PhD student, and I will talk about half or so of his thesis, which he finished a year ago or so. What is it about? I think many of you have heard about cavity physics and cavity chemistry. So in our case, we are interested in cavities. So think of them as two mirrors. And inside we have molecules. So this is molecular cavity chemistry. And the cavity itself supports electromagnetic waves, standing electromagnetic waves. And these can couple to molecular modes. If this coupling is strong, I'll specify this in a minute, then one forms sort of hybrid states between matter and the electromagnetic waves, and these are called polaritons. And this field has been established in chemistry, at least on the molecular level, since about 10 years now, mostly by people like Ebbesen in Strasbourg. So for instance, if you have a molecule and you describe a vibration along a certain vibrational coordinate, then we typically describe this by some sort of Morse potential, and we have the vibrational levels here embedded. And then if you put this molecule into a cavity, here you have the cavity modes. If they are harmonic, then they are equally spaced with 0, 1, 2 quanta in there. And then if you switch on a coupling, and if this transition here is resonant with the molecular mode, then you get a splitting of this V = 1 level into 2 levels, called the lower polaritonic state, P-, and the upper polaritonic state called P+. And the energy difference between them is the so-called Rabi splitting. And as I said, if the coupling is strong enough, then this splitting can be seen, for instance, in vibrational spectra. So in this case, we form so-called vibropolaritons. We see Rabi splittings in vibrational spectra. Typically, the splitting is in the order of tens of wave numbers. Here is a molecular example studied by the Ebbesen group. For instance, it's a rather complicated molecule. And if you look at the infrared spectra, you get all sorts of peaks. For instance, here for the silicon carbon bond, that would be this bond here, or you also have a silicon oxygen bond here. And this is the spectrum without a cavity. And if you put the molecule into the cavity, then, for instance, the silicon carbon signal splits into the lower and upper polaritonic state, nicely seen here. Or if you change the frequency of the cavity, then you also see, for instance, the splitting of the silicon carbon bond in lower and upper polaritonic states. You can also do chemistry with this. For instance, Edison have shown that they can selectively split either the silicon carbon bond or the silicon oxygen bond in this molecule, basically by tuning the frequency of the cavity mode. So in other words, by changing the distance between the two mirrors, for example. So our control parameters to achieve, for instance, mode selective chemistry are the cavity frequency, let's call it omega c, and of course the molecule cavity coupling strength eta, which I will define in a minute. And typically one speaks of strong coupling, in this case, strong vibrational coupling, if we couple to vibrations. We speak of strong coupling if this eta parameter is 0.1 or so. And if it's larger than that, one achieves the so-called ultra-strong coupling regime. There is also the possibility that you couple these cavity modes, not to vibrations, but to electronic states of the molecule. This gives then rise to electronic strong coupling. In this case, you form electronic polaritons. So these are hybrid states of molecular electronic excitations and the electromagnetic waves of the cavity. You also get Rabi splittings in this case, can be seen then in not in vibrational, but in optical spectra. And there the splitting goes up to thousands of wave numbers. And one also changes, in fact, the excited state topology and the resulting photochemistry in this case. Here's an example for a molecular switch. That molecule is called spiropyran. That one is called myrocyanine, and you can switch from one state to the other, changing the properties of the molecule, its color, and other properties. And here is the usual thing when you start, for instance, from this myrocyanine form, you can excite it to some excited state, and then you can induce some photochemistry, and it eventually would end up in the spiropyran state. If you bring the molecule in a cavity, here's an experimental realization how this is done. Then, for instance, when you start from the myrocyanine side, the higher excited, or the first excited state splits into this lower and upper polaritonic states again. And the photochemistry which results is totally altered. And in this case, one finds that within the cavity, you see a measure for the reactivity from this molecule to this molecule as a function of time. And in the cavity, the reaction in this case is slowed down. So the cavity makes the reaction less likely. Of course, we would rather like to have the situation where we accelerate the rate and the reactivity, but I will talk about this point later on. Also here, we have, again, the frequency of the cavity as a control parameter. The coupling strength is interesting. And of course, these excited states typically have also only a certain lifetime. And also the cavity itself is not perfect typically, so it loses energy, so it has a finite fidelity, as it is called. And there is a connection between what I considered so far, so molecules in cavities, typically realized by a Fabry-Perot cavity, and plasmonic chemistry. And in fact, it's pretty much the same. There are some differences in the polarization of the electromagnetic field in both situations. But other than that, plasmonic cavities or plasmonic particles itself, the plasmon itself, it behaves very similar to a standing wave in such a cavity. So if you understand this cavity physics and chemistry, you also have hope to understand these strong coupling effects in plasmonic arrangements. Again, so we have an influence on spectroscopy. We can alter grounded excited state reactivity, and many other properties have been controlled by these cavities. For instance, the intramolecular vibrational energy redistribution, intersystem crossing rates, internal conversion rates. One can hope to control charge transfer in molecules due to cavities, and even the transition temperature from a normal conductor to a superconductor, for instance. And so this is a fascinating field. And we also try to make some contributions from the molecular side to understand certain things, and many things are still not understood. So I will talk in this presentation first a little bit about the quantum mechanical foundations of molecular cavity chemistry. Then I will speak about these vibrational polaritons all the time, and their formation and their influence on infrared spectra. We will talk about rates in the electronic ground state. There will be a small detour about the Born-Oppenheimer approximation in the context of cavity chemistry and physics. And I will also talk a little bit about reaction control. Well, some foundations. I don't want to go into detail, but the starting point is the following. We have a Hamiltonian comprising of the electrons, the nuclei of the molecule with masses Ma and charges, nuclear charges Za. Then we have the coupling between the two entities in the molecule, the electrons and the nuclei. And then we also have the cavity Hamiltonian, and that describes the standing electromagnetic waves within the cavity. And so we describe this by a vector field, A, which then ensures the coupling between the cavity and the molecule. And the cavity itself is described as a set of harmonic oscillators with a certain polarization lambda. And there may be several of these cavity modes with characteristic frequencies omega c. And a dagger and A are the usual creation and annihilation operator of the light field. So we treat the light fully quantum mechanically. And that turns out to be also quite important. Then there's a lot of formalism. One uses typically the Coulomb gauge and the length gauge representation, and there's the dipole approximation or long wavelength approximation. One adopts what is called the Power-Zinau-Woolley transformation, very complicated stuff. And then one, at least for me, then one comes up with a Born-Oppenheimer type approximation, which separates nuclear from electronic degrees of freedom. And the result of all of this is what one calls the molecular Pauli-Fierz Hamiltonian. So if you have one molecular mode only, a vibrational mode, for example, call it Q, then we have a potential V of Q. This is then our Morse potential, kinetic energy operator. Both of them comprise the molecular Hamiltonian. Then we have the cavity field. And the cavity itself is described then as a harmonic oscillator. In this case, I consider only a single cavity mode. And we introduce here a displacement coordinate for the light, xc, which depends on these creation and annihilation operators, and a corresponding momentum. So this is nothing but a harmonic oscillator, if you wish. And then you have the coupling of this harmonic oscillator to the molecular mode. This is achieved by this term. And what we have here is the dipole moment of the molecule along the vibrational coordinate. And this comes in linear and in quadratic form. And this quadratic form is called the dipole self-energy. G, by the way, is the coupling constant. From the physical dimension, it's a field strength, volt over angstrom or whatever you wish. And this coupling constant depends on the size of the cavity. So how far are our two mirrors apart, or how large is my nanoparticle? It depends on the cavity frequency and also on properties of the material within the cavity. Often one works instead of this field strength with a dimensionless coupling constant eta, which I introduced already earlier. And this contains then the transition dipole moment between a vibrational state I, initial state, to a final state F, for example. And in general, this coupling constant increases with the square root of the number of molecules within the cavity. Okay, so this is the formalism. And now if you look at this Hamiltonian and you gather all terms which depend on coordinates only, then you can define a cavity Born-Oppenheimer potential energy surface. So in our case, with one molecular mode and one cavity mode, this would be a two-dimensional surface rather than a one-dimensional one, containing all these four terms: molecule, light mode, and then the two coupling terms, including this dipole self-energy term. So let me give an example. Here we have a simple model of the ammonia molecule. And typically we describe this as a symmetric double well potential in textbooks. So we have here the situation along the umbrella coordinate where the hydrogens point down. Here the hydrogens point up. There's a barrier in between, about 2000 wave numbers high. And this double well potential supports the typical tunneling doublets, 0 plus, 0 minus, 1 plus, 1 minus. And here in red is a dipole function for this molecule, which changes sign when you go from this to the inverted state. Now, this one-dimensional potential curve V of Q becomes a two-dimensional potential energy surface in this case. And here we just have added this term, a harmonic oscillator along the light coordinate. Here is the molecular coordinate. And this is for the case that we have no coupling eta between the two degrees of freedom. And this is the situation where we switch on some coupling. And you see here in red also some reaction path, which of course is quite different from the reaction path in the uncoupled case. And these potential energy surfaces, you can use them as any potential energy surface, which we are used to in molecular physics. We can use it to compute polaritronic spectra, reaction dynamics, kinetics, and so forth. The first questions we asked ourselves, however, was, okay, we have now these two-dimensional potential energy surfaces, for instance, for a lithium hydrogen molecule or an OH molecule here in black. We have the dipole moments. So we can construct this cavity potential energy surface with one light mode coupled to it. In the case of lithium hydride without a cavity or with the cavity included. And as I said, the potential energy surface then changes. And the first question was, does this have any influence, for instance, on the bond length of the molecule or the dissociation energy? So are the ground state properties affected by putting the molecule into such a cavity? And the answer is no, usually not. So here, for instance, we look at the distance, the bond length between lithium and hydrogen or oxygen and hydrogen. And we do this one case when we include this dipole self-energy term, quadratic, in the dipole moment, or we neglect it. When we neglect it, we get, in fact, some effect on the bond length, but this is artificial, because if you take it into account, this other term, then there's basically no dependence of the bond length on the cavity strength coupling strength. The same holds true for the dissociation energies. There's basically no effect, at least for realistic values of coupling strengths. Now we use the whole thing to do spectroscopy. And let me talk about this lithium hydride molecule again, where we only take the distance between lithium and hydrogen into account. So here we have again the molecular mode. Here we have the light displacement mode. And here we have the situation that there's no coupling. So we have here the ground state, which has no quantum in the vibration and no quantum in the light mode. So 0 photons, so to say. Then here we have a doublet. So we choose a resonance frequency for the cavity frequency. So it should be in resonance with the 0 to 1 transition of the lithium hydrogen molecule. And here we have one node along the Q coordinate. So this is vibrational excited molecule, but no light mode. And here we have the situation that the molecule is still in its vibrational ground state, but we have one photon in it. Here we have doubly excited states, 3 of them, 2 excitations in the molecule, or 2 excitations in the light, or 1 excitation in the light and 1 in the molecule. So these states are basically degenerate, these excited states. But if you switch on the coupling now, they split. They split up into lower and upper polaritonic states, or in this triplet situation in a lower, medium, and upper polaritonic states. And these states, they are curved. So they are mixtures of light and matter. These are these famous vibrational polaritons. And the splitting is the Rabi splitting again. And that can be seen in spectra calculations. So you can use a time-dependent approach and calculate a correlation function. So here, for instance, we have for lithium hydride, when you have no coupling, a single peak or a 0 to 1 transition in the molecule. But if we then ramp up the coupling between system and the environment, the cavity, then we get 2 peaks, and the splitting depends on the size of the coupling strength. You can also do this, of course, then for other molecules, like for ammonia, which I showed you before. And there the spectra are a little bit more complicated due to the doublet structure already of the system states. You have these tunnel doublets, but you can also nicely calculate and explain the Rabi splitted spectra there. We have done this then even for higher dimensions. So here we have a situation where we have a CO molecule, carbon monoxide, in a cavity. So 2 atoms in a cavity, that comprises actually a 6-dimensional problem. But we fixed 3 coordinates. The center of mass of the molecule was fixed. So X, Y, and Z positions of the molecule were fixed. But the molecule was allowed to vibrate, and it was allowed to rotate along 2 angles, theta and phi. And we also did not take only one cavity mode into account, but a perpendicular one as well. So we have 2 different polarizations, transversal polarizations. So altogether, this is then a 5-dimensional problem which we have. And one has to solve a 5-dimensional Schrödinger equation, either time-dependent or time-independent. And one gets funny stuff there, which is actually also known already from literature. So here, for instance, one gets some sort of potential energy surfaces. These are vibrational potential energy surfaces for the first excited state of the molecule. So either 1 quantum in the R mode, in the vibrational mode, or 1 quantum in the one cavity mode, or a quantum in the other cavity mode. And if they all mix together, you get these funny structures. You get 3 potential energy surfaces, so to say, as a function of theta and phi, the rotational angles. And this is nothing but conical intersections. And in fact, these vibrational polariton-induced conical intersections. They have been predicted some time ago by Wiebeg and Zederbaum. Normally, you would not see such conical intersections for a diatomic molecule because you could only see avoided crossings there normally. So you need a higher dimensional thing, but there's the possibility to put light in there. Then you get the so-called light-induced conical intersections. And this is a special variant of this, if you wish. It's a vibrational polariton-induced conical intersection. One can then also calculate spectra there. And in the end, you get then some spectra which also show these Rabi splittings. But in addition, you get some rotational progression as well, which can be discussed. But this is a thing which I won't emphasize here too much. In all of these cases before, when we calculated infrared spectra, we tried to solve the underlying Schrödinger equation, time-dependent or time-independent, exactly. And this is very cumbersome when it comes to high-dimensional problems like polyatomic molecules. What do you do then? Well, in quantum chemistry, we know how to do this. One does then usually the so-called double-harmonic approximation. You assume that the n-atomic molecule has 3 n-6 vibrational modes, and they are idealized as harmonic oscillators. And then you assume that along these harmonic oscillator modes, the dipole moment is linear. And both together then gives vibrational spectra in the sense that one sets up a so-called Hessian, that is the potential of the molecule and the second derivatives taken from there. And if you calculate the eigenvectors of the Hessian, then you get the so-called, the eigenvectors are called the normal modes then, and the eigenvalues are the squared harmonic frequencies of the molecule. So that is what is done in every quantum chemistry program, Gaussian, Molpro, Orca, whatever. Here is an extension when the molecule is in a cavity. Then in addition, you have a Hessian block, which corresponds to cavity modes, 1, 2, or more than that. And we have some coupling terms in between. So instead of 3n-6, we get 3n-6 plus nc, where nc is the number of cavity modes. And then you get to these frequencies as well. And that is done, so we have written a little program which does this. And then you can apply, at least in this double harmonic approximation, or you can calculate infrared spectra for more complicated molecules. Here's one where we have a benzonitrile molecule, C6H5Cn, so quite many modes. And here in red are the calculated ones, showing some Rabi splittings for the Cn mode and for some CH mode. And in blue is the experiment. In blue, you see also the modes of the cavity, which we don't see here because we did not include this in our dipole model. But we do see the molecular modes, which are split according to this Rabi splittings. Okay, let me briefly talk about reactions. And let me return again to this ammonia system, where we already saw this double well structure of the molecular potential corresponding to the NH3 down and NH3 up configurations, and where we coupled a single cavity mode to it, giving rise to these two-dimensional potential energy surfaces. I already told you that the reaction path in going from here to here looks, in this coupled case, quite different from this one. You may ask the question, well, perhaps also the barriers change? And what does the different reaction path then do with the reaction. Well, we try to do this by quantum rate theory. So what we calculate is a so-called cumulative reaction probability. So this is the probability to get from left to right as a function of total energy E. And in our case, it will also depend on this cavity molecule coupling strength eta. This is then Boltzmann weighted, and then the prefactor here contains the reactant partition function, which basically tells you how many states, quantum states, can react in the first place at a given temperature T. And the cumulative reaction probability we calculate by a Green's function method. This is well established in the literature, and this is basically exact rate theory for this system. And then we get a rate constant K, and measured in seconds to the -1. And then we do what every physical chemist would do. We plot ln K versus 1/T. So we make this Arrhenius plot. And in a classical context, then you get simply then the usual linear behavior. And from the slope, you can then find out about the barrier height. And from the intercept with the y-axis, you learn about the prefactor. And well, here we get this linear behavior, first of all, only at high temperatures, but then we go to low temperatures, and there we see a clear deviation. That is the tunneling regime. So here, the reaction from left to right goes via tunneling. But now let me see what the cavity does. So the dark blue curve is without the cavity. And then we switch on the cavity, and you see that the rate goes down the higher the coupling is. So we have a negative effect on the rates, as Ebbison observed in many cases, of the strong coupling. And why is this negative effect there? Well, first of all, we can look at these reaction paths, which I showed you before. And we see that along the reaction path, the barrier gets, first of all, broader. It does not get higher, interestingly, at least not in this cavity Born-Oppenheimer approximation. So the barrier stays the same. So if you would apply Arrhenius, you would see no effect on the rates, but it gets broader. That reduces the tunneling. And the second thing is you not only have this direction along the path here, but you also have the perpendicular mode. And this perpendicular mode gets stiffer the higher the coupling is. And therefore, these cumulative reaction probabilities, NFE, they always show such a step-like behavior. They are shifted to higher energies. You need more energy to really overcome the quantized barrier, so to say. And well, one thing we were interested in, is this really true? That here the barrier is not affected at all. And as I said, this has to do with the Born-Oppenheimer approximation. And you may have seen this movie some time ago, where then the actors say, okay, Heisenberg says to Oppenheimer, I read your very interesting paper with Born about molecules. So this was the origin of the Born-Oppenheimer approximation. In Born-Oppenheimer approximation, we are used to separate nuclei from electrons in molecules. And this gives rise to potential energy surfaces, ground state, first excited state, as a function of nuclear coordinates. And if we want to go beyond the Born-Oppenheimer approximation, well, then we get two effects. One is that the potential energy surfaces are modified a little bit. These are called the diagonal Born-Oppenheimer corrections for every potential energy surface. And they also start to be coupled. These are the non-adiabatic coupling elements between states I and J due to the coupling of the electrons to the nuclei. Now we have a cavity in addition. And a cavity has its own frequency, namely the cavity frequency. And the cavity frequency may be large or small, depending on if you have electronic strong coupling or vibrational strong coupling. In vibrational strong coupling, the cavity frequency is of the order of vibrational frequencies of the molecules. So we expect that the Born-Oppenheimer approximation will be good. But you have to take into account that in addition to this coupling between nuclei and electrons, you also have the coupling between electrons and cavity modes in a cavity. And how good is then when we neglect this and this and also this, because that would be the the crude cavity Born-Oppenheimer approximation. And in order to study this, Eric Fisher then looked at this model system. It's called the Shin-Matthew model. Now one puts it in a cavity, then it's called the cavity Shin-Matthew model. That is a very simple model comprising of 3 protons. 2 of them are fixed, and the middle one moves along this line with the coordinate capital R. And then there's 1 electron having a coordinate small r. So that would be a 2-dimensional problem. Now, in addition, we also have a cavity mode. So the full problem would be a 3-dimensional wave function. And in the Born-Oppenheimer approximation, we fix now 2 of them, the nuclei and the light mode, and we only solve an electronic Schrödinger equation. And we can solve this 3-dimensional Schrödinger equation exactly and compare and calculate these matrix elements for the coupling. For instance, in this Shin-Matthew model, we get 2 states, V0 and V1. As a function of R, capital R, and the light mode. And here are the couplings between the 2. First, due to the coupling between nuclei and electrons, these are the normal non-adiabatic coupling elements. And here we have the same for the coupling of the electrons to the cavity mode. They look pretty much the same. However, if you look at the scale, this is 10 to the minus 2, this is 10 to the minus 5. So they seem to be much stronger than the usual non-adiabatic coupling elements. And then the other effect was, as I said, you have not only the couplings, also the potential energy surfaces themselves are somehow changed when you go beyond the Born-Oppenheimer approximation. And in fact, for the ground state, with this double minimum potential, we calculated the deviation of this, introducing or going beyond the cavity Born-Oppenheimer approximation from the case where we don't do it. And this was done for different coupling strengths. This is the barrier height when we apply the crude cavity Born-Oppenheimer approximation. No effect on the barrier, as we have seen before. But if we include non-Born-Oppenheimer effects, you get a few % effect, but this is not all too huge. So we also studied another system, I should say, where we have a positive effect of the cavity on the reactivity. That is something which chemists like more, I guess. And so this is a hydrogen transfer example for a molecule called thioacetyl acetone. So this is shown here, and it has an OH bond here and a CS bond here. That is one configuration. That's the low energy state, described in a double well potential, in an asymmetric double well potential in this case. And then there's also a minimum corresponding to a higher energy state where the hydrogen has jumped from the oxygen to the sulfur atom. So this is this thiol configuration then. And in the literature, there was a 2-dimensional potential energy surface around for this molecule, which we took. These 2 dimensions are, one is the hydrogen transfer coordinate, so basically this coordinate along here. And then there's a coordinate capital Q that has to do something with some collective motion of the other molecules. So you get this two-dimensional potential energy surface, and if you diagonalize the corresponding Hamiltonian, you get a ground state, which is localized in the OH configuration. So that would classically correspond to this isomer. And then the first excited state, which is still below the barrier, there's a barrier of 1600 wave numbers between the two states. So this one is still below the barrier, but this would correspond with this situation. Okay, so this is the situation without a cavity. Now we put the molecule in a cavity. And so we start with 0 photons in the cavity. And we start in the ground state of the OH configuration here. And we want to go there. And we can calculate switching probability from here to here by just by solving the time-dependent Schrödinger equation using this non-stationary initial state, and then see how the population flows to the other side. So typically one gets the oscillatory behavior because the wave packet then also comes back again. But interesting is the first part here. And here from the slope of these curves, which belong to different coupling strengths, very small coupling strengths and very high coupling strengths. From the slope, you see that the higher the coupling is, the faster the molecule goes to the other side. So without coupling, we have no reaction. With coupling, we get some reaction, and the reaction gets faster. The stronger the coupling is. So this is a positive control of a reaction. We also played a little bit by putting now photons or exciting the cavity mode. So we put 0, 1, 2, 3, 4 photons into the cavity mode. In this case, there's only a small effect, at least on the initial slope here. In fact, if you go to longer times, it seems that putting more energy into the cavity has even a bad effect on the performance of the reaction. And one can also explain this with simple arguments why this is so. Well, what we then also tried was to use so-called optimal control theory. There's a theory called direct optimal control, where one not only optimizes electrical field. So we now really send in photons. So I leave now my original title, Photochemistry without light, because now we use really classical light to control the cavity molecule system. And we start from the ground state. That is now a one-dimensional model for this molecule. The second coordinate is now the light coordinate. And we use the one-dimensional model here for the molecule, which gives pretty much the same results, by the way. And we have certain excited states. And if you linearly combine these two excited states, you get a state which is then in the other well. So we want to go from here to here. And we use this direct optimal control theory. And this gives us not only an optimal electric field to go from here to here, and analyze the field components. You see it has two parts, can analyze the frequencies and so forth. And you see that this field then really does the job. So we want to go from the ground state, this is orange, population in orange goes down. And we want to reach the target state, which is this blue state, and that goes up as desired. And one not only then controls the field, but you also get a message about the optimal control strength, which we could, for instance, change by changing distance between these two mirrors in the cavity. Okay, so there's the possibility to control this reactivity in addition to the cavity parameters, also with classical light field parameters. This is the message of this work. We also then went beyond the single molecule situation, which is sort of artificial because in reality, in most experiments at least, You have many molecules within the cavity. So you have an ensemble, not only a single one. And here's a situation where we have 20 molecules of this TTA type, this thioacetyl acetone in a cavity. And so we solved then a multi-dimensional Schrödinger equation. So we have one cavity mode. Each molecule is described by a single transfer mode. So if we have a 20 molecule situation and with this one cavity mode, we have to solve a 21-dimensional Schrödinger equation. And that is not so easy, but there are techniques around to do this. We use, in particular, the so-called multi-layer, multi-configurational, time-dependent artery method. And then it's possible to solve this high-dimensional Schrödinger equation. And here we have, again, the probability to be not on the original OH side, but to go to the SH side as a function of time for different ensemble sizes. And you see it's complicated. So it is not just additive effects or something. We analyzed this behavior in some detail. The thing is, if you have more molecules, you get, so this is the single molecule case, you get more reaction probability. But beyond this, it is hard to say what the different molecules do. So there are strong non-additive ensemble effects. And in fact, we can see some effects of entanglement there as well. Okay, that was basically all I wanted to tell you. There are a few take-home messages from this talk. I introduced you this Pauli-Fierz Hamiltonian for vibrational strong coupling in our case. I would say at the moment in chemistry, this is the most used Hamiltonian. It has some approximations in it, but it is easy to combine with ordinary quantum chemistry to make, then to describe the dynamics of molecular systems in cavities. One of the applications I was talking about was the calculation of infrared spectra, and first of all, the formation of the vibrational polaritons. We started with very simple models, one-dimensional with one cavity mode, and up to a three-dimensional plus two cavity mode system, where we had the concept of row vibrational polaritons and these vibrational polariton induced conical intersections. Then, if you want to go to even more complicated systems, it is good to extend to these classical approximations of quantum chemistry, making use of the harmonic approximation for vibrations and the linear approximation for dipole moments, also to the cavity case. And then we talked about reactions, which you can describe with time-dependent and time-independent mechanisms. We saw an example for ammonia where we had a rate decelerating effect of the cavity. We saw an example where we have a rate accelerating effect. That was this hydrogen transfer problem. And I was talking also about the possibility to control the reactivity of molecules in cavities. And finally, as a side note, the Born-Oppenheimer approximation becomes a little bit more complicated and subtle when you have, in addition to the electrons and the nuclei, also a cavity mode. So I thank you for your attention. Here are some possible extensions which we work on at the moment. When we go to higher dimensions, include dissipative effects and do a little bit more control. And I would like to thank my group, in particular, Eric Fischer, that's the one here. He did basically all the work I was talking about today. Thank you very much for your attention.
Thank you very much, Peter, for this enlightening talk. So time is open for questions. Let me just remind that If anyone online wants to make a question, please send it to the chat or to the question and answer section, and I will read them. Go ahead.
So, nice talk. So, one question: when you analyze the rates in your chemical reaction,
Yes.
you always put this eta factor.
Yes.
So, my question is, how realistic is this eta factor for just a single molecule? Or are you assuming
Yes.
that everything scales as the square root of the number of molecules?
Basically, yes. You are right. For a single molecule, the eta would be much too large. But you have this, it's in simple theories, at least square root n behavior of the effective coupling. And there are experiments beginning now, in fact, with single molecules in cavities. So even there, you can obviously, in some cases, see some strong coupling effects. But in general, you have to use a liquid or something with many molecules inside, and then this is more of a model study. Yes, it's not super realistic.
Yeah, because at the end of the talk, when you put the results for 20 molecules, it doesn't seem
There it seems more complicated. When we do this, however, for the infrared spectra, there we have this method with this double harmonic approximation. There we really were able to compare one molecule with n molecules, and then also with a scaled one molecule approach where we had this square root n scaling in there. There was also almost perfect agreement for this one system we studied. For the reaction rates, I'm not quite sure. So it is really true. I think one has to go to these cavity ensembles. But you could treat then perhaps the nuclei at least, or the molecules classically. So you would have a semi-classical description, and that should also be possible.
Thank you.
Thanks for the talk. I have a question to this Born-Oppenheimer approximation. Can I understand it analogously to what people do when they treat Jahn-Teller systems, that you kind of do Jahn-Teller and then you add these Fij non-adiabatic couplings kind of in a second step?
Yes, yes. Jahn-Teller and Born-Oppenheimer are closely related. And in the original Born-Oppenheimer approximation, you just have these potential energy surfaces. So you solve an electronic Schrödinger equation at a given nuclear configuration, then you change the nuclear configuration, and then you get energies at different points. And so you solve a much lower dimensional Schrödinger equation. Now, you can use this as a starting point and for these non-Born-Oppenheimer corrections. And it turns out that you get then corrections to the diagonal elements, that is this potential shifts. And in particular, you get these non-adiabatic couplings, and the Jahn-Teller is related to this non-adiabatic coupling stuff. And the alternative would be to solve the full dimensional Schrödinger equation with electrons and nuclei, that you can do for some simple systems, H2 plus, H2 maybe, and this Schieden-Matthew model, for instance. But that should be equivalent to this approach if here you are converged. So you need really many of the excited states.
Yes. Thanks a lot for the talk. I was wondering if there is any understanding on what kind of processes gets accelerated and what gets retarded when you couple molecules to a cavity or different kinds of cavities.
Yeah, very good question. So Epperson, he published a paper some time ago where he has a table with molecules they studied, and he grouped them according to accelerating effect and de-accelerating effects. Well, I guess you have to look at the coupling, the shape of the dipole function in the end to explain things. Originally, I thought, okay, a cavity should always help, but why should it help if you think of it? I mean, normally, now I think in normal cases, you would expect that the cavity does not help. It should decelerate the chemistry. Why? Because you just have, if you have a molecule and you excite it from a ground state to an excited state, and you have an oscillator of the cavity nearby, and they are resonant, if you put energy here to overcome a barrier or something, the energy can leak out now into the cavity. So for me now, the negative effect of the cavity is more intuitive than a positive effect. Yeah, but I'm afraid I cannot fully answer your question. But I guess one has to look at the shape of the dipole function, which in effect then determines how these curves here, for instance, these potential curves look like.
Thank you.
Yes.
Sorry, I am experimentalist, so maybe my question would be naive. I would like to ask you about actually referring to the title of your talk. Without photons, without light.
Yeah.
As far as I understand, that comes to the Hamiltonian for cavity, where there is no creation or annihilation operators, but have a term 1/2.
Yes.
So this 1/2 will keep there. And my question is, if you put, let's say, ammonia in cavity, just wait a little bit, and then what? If we analyze product or opening cavity, would you expect some reactivity in that case? Without
Well, these are very good questions. First of all, what is light? Okay, so a cavity, if you have, in the quantized case, you can have 0 photons in there. You can have a photon number. You can calculate this. So you calculate the expectation value of this A dagger A, and that can be 0. Still, there will be an effect on the molecule, but you can also put photons inside so that you have then a photon number different from 0. But is this already light? For me, this is a standing light wave. Okay, some sort of light. But for me, light is always also propagating. So, okay, that is now probably semantics. So, but coming back to your question, I think you have effects even if there is not a photon in there in the cavity. But the effect is, of course, smaller compared to situations where you have photon numbers which are different from 0. And what happens to an ammonia molecule? I think, if you just put this molecule into the cavity, I mean, if you look at these potential energy surfaces, okay, that would be then the situation. I would guess it is more stable against the inversion, at least in the low temperature regime. In the high temperature regime, you should see almost no effect because the barrier height is still pretty much the same, only small effects on the barrier height. And therefore, the over the barrier process is hardly affected. At low temperatures, you would see probably a smaller isomerization rate. That would be my expectation.
Thank you.
Okay, time for any other last question? Because if not, we can close the session here with this very philosophical question about what is light. What is reality, right? So then we can leave that for lunch time. So thank you very much, Peter, again for this talk.